In this video, we want to learn about one of the trigonometric substitutions. Here, we want to learn about this substitution. X equals a secant theta. But when we use this substitution, whenever in the integral that we want to find, we have this expression, a square root of x to the 2 minus a to the 2. And this expression can be in the numerator of the expression or in the denominator. It doesn't matter. We can use this substitution for finding integrals that have this expression in the integral. And the idea behind this substitution is that we want to get rid of the square root. But before using this substitution, always it's better idea to first try the normal u substitution. Suppose the expression inside the radical as u, and if the derivative of u is outside of the radical, then you can find probably the integral with the normal substitution, and you don't need to use this substitution. We use this substitution when the normal substitution, the normal u substitution doesn't work, because this is a little advanced and a little complicated method for finding integrals. Let me show you in general, if we substitute this for x here, what happens? If we substitute x with a secant theta, then we have a square root of x to the 2 is a to the 2 secant to the 2 theta minus a to the 2. We can factor a to the 2 from these two terms, and we can pull out a to the 2 to the outside. If we factor a to the 2, then we have a square root of a to the 2 times by secant to the 2 theta minus 1. A square root of a to the 2 is a. Again, let me mention that we suppose a to be positive number, and so when we want to find a square root of a to the 2, we don't need to put absolute for a. We suppose a positive number, so we can move the a to the 2 to the outside and write it as a. So this equals a radical secant to the 2 minus 1. Now remember one important identity that we have for secant to the 2 minus 1. This is very important identity that we need for this substitution to remember. Secant to the 2 minus 1 is tangent to the 2 theta. Based on this identity, we can replace this with tangent to the 2 theta. What is a square root of tangent to the 2? A square root of tangent to the 2 is absolute of tangent theta. So this equals a absolute of tangent of theta. And why we have to put absolute for tangent of theta here? Because tangent, as we know, can be positive or negative. And when you take a square root of tangent to the 2, the answer needs a absolute. Now please attention to these details. These are really important, because in this substitution we suppose this theta to be between 0 and pi over 2. In this region we know that in the first quadrant, this is the first quadrant, we know that the tangent is positive. So when theta is between 0 and pi over 2, we don't need to put absolute for tangent theta, and simply we can replace it with tangent theta. But what about the other case? What about these two intervals? Please pay attention. In some textbooks, they consider theta to be between pi over 2 and pi. In this is the second quadrant. In second quadrant, tangent is negative, so you need to keep absolute here. But some textbooks consider theta to be between pi and 3 pi over 2. This is the third quadrant. And in the third quadrant, tangent is also positive. So I recommend you to always keep theta in these two intervals. Theta between 0 and pi over 2 and theta between pi and 3 pi over 2. If we follow this rule that we always keep theta between 0 and pi over 2 or theta between pi and 3 pi over 2, then we can completely get rid of the absolute. And we don't need to put absolute for tangent theta. And this makes the calculations easier. Let's review the process from the beginning. Whenever in an integral we have this expression, first we try u substitution. We suppose the inside as u, If the derivative of u is outside, if we have x here, because the derivative of inside is 2x, if we have x or 2x, then we can find integral without this substitution. But if that method doesn't work, then we use this substitution. X equals a secant theta. So in the integral, we replace x with a secant theta. By this substitution, this radical, all of this radical is equal to a tangent theta. You can keep this in your head and you don't need to do all of these calculations for every single question. Radical x to the 2 minus a to the 2 is always a tangent theta. So for example, if in a question we have radical x to the 2 minus 100, then by this substitution, which is x equals 10 secant theta, this radical would be equal to what? It equals to 10, because a to the 2 is 100, so a is 10. So this radical is equal to 10 times by tangent theta. And you don't need to substitute 10 secant theta here, raise it to the 2, minus this, use the identity, and so on. Immediately you can say all of this radical is 10 tangent theta. Let me explain one more thing here, and then we can start doing some questions to learn this technique fully. Attention that if x to the 2 appears after a to the 2, if we have a to the 2 minus x to the 2, then for this we have to use the other trig substitution, which is a sine theta. And if between these two we have a plus, if you remember, for x to the 2 plus a to the 2, or a to the 2 plus x to the 2, in when we have addition here, when we add these two, it doesn't matter the order, then we use the other trig substitution, which is a tangent theta. So be careful about this, to not mix these substitutions with each other. Whenever x or the variable appears first, x to the 2, then minus a to the 2, then we use this substitution, and by this substitution all of this radical simply is a tangent theta. And let me add one more thing. This is the last thing that I have to mention. When you choose x as a secant theta, because you want to replace, you want to substitute everything in terms of theta, you need to know what is dx. If x is a secant theta, what is dx? What is the derivative of x? The derivative of the other side is a. The derivative of secant is secant times tan. And don't forget to multiply it by d theta. So this is the other thing that you need to solve the integral. Now that we went briefly over everything necessary for this substitution, let's do some questions. The first example here is integral of dx over x to the 2 is square root of x to the 2 minus 25. In this integral, first we try to use the normal substitution, u substitution. We suppose the expression inside the radical as u. If we suppose u as x to the 2 minus 25, then we can see that du is 2x dx. But the problem is that we don't have x times by dx in numerator. So if we solve this for dx, then dx would be du over 2x, and if you try to substitute this in the integral, you would see that this doesn't work. Again, why this substitution doesn't work? Because when we are finding the derivative of du, which is this expression, we expect to have x times by dx. Do you have x times by dx here? This x to the 2 is in the denominator. No, we don't. We need x times dx. So now that we know that the normal substitution doesn't work, we use the trig substitution. And because it is x to the 2 minus 25, and attention, 25 is basically 5 to the 2. So what is the trig substitution that we want to use for solving this? X equals a secant theta. What is a here? 5. X equals 5 secant theta. And as I explained in the beginning of the video, by this substitution, all of this radical would be what? All of this radical equals to 5 tangent theta. If you remember, always this radical equals a, which in this case is 5 tangent theta. You don't need to do the calculation again and again and again for every single question. 5 tangent theta. And what about that dx in numerator? That dx is derivative of x, derivative of this, which is 5 secant theta tangent theta d theta. Now everything is ready to be substituted in this integral. For dx, we substitute 5 secant theta tangent theta d theta. X to the 2. What is x? X is this. X to the 2 would be 5 secant to the 2, which is 25 secant to the 2. This radical is 5 tangent theta. Now look at the numerator, look at the denominator, try to find common terms, cancel them. 5 with 5 cancels from numerator with denominator. This 5 with this 5 cancels. Tangent with tangent cancels. Secant with 1 secant from denominator cancels. What remains? We have a 25 in denominator. We can move it to the outside. So this equals to 1 over 25 integral. Again, tangent with tangent cancels. 1 secant with secant to the 2 cancels. And 1 secant remains in the denominator. So basically we have d theta over secant of theta. But attention, 1 over secant is basically cosine theta. Because remember, what is secant? Secant is 1 over cosine. So basically here we have 1 over cosine. Reciprocal of cosine is cosine. So here this equals to 1 over 25 integral of cosine theta d theta. Now for this integral of cosine is sine theta. So this equals to 1 over 25 sine theta plus, and this is the answer of the integral. But the original integral that we had here is in terms of x, but the answer that we have is in terms of theta. So we have to try to rewrite sine of theta in terms of x. And remember, by this formula, x and theta are related by each other. So it's possible to write sine of theta in terms of x. And the best way to do this is to use a right triangle. Let me write right triangle here. Based on this relation here, what is secant theta? Secant theta equals x over 5. But we know that secant is 1 over cosine. So 1 over cosine theta is x over 5. Here, if we flip this side, if we move cosine to the top, 1 to the bottom, and if we flip the other side, if we flip both sides of this relation, simply we can get this cosine theta is 5 over x. So in this right triangle, if we suppose here theta, cosine is adjacent, so 5 over hypotenuse x, so 5 over x. Here we need to find sine theta, but sine is opposite, so we have to calculate this side. For finding this side, we use Pythagorean theorem. So let me suppose this as a, for example. Then by the Pythagorean theorem, a to the 2 plus 5 to the 2 is x to the 2. And if we solve this for a equals a square root of x to the 2 minus 25. Move these to the other side and take a square root. So this side of this triangle is, this side is radical x to the 2 minus 25. Now we can find sine. Sine of theta equals opposite over hypotenuse. So we have 1 over 25 times by opposite side over hypotenuse plus c. So the answer of the integral can be written in the form of, if we multiply numerator by numerator, we have radical x to the 2 minus 25, and in the denominator we have 25x plus c. This is the answer of this integral here. The answer of this integral is this. By doing some examples, you can see that this process is long, but it's not really hard. As long as you know that what substitution to use and you can memorize this, then the other part of the process is a repeating process. Let me show you some more examples. Here we have integral of dx over radical x to the 2 minus a to the 2. This is a very famous standard example for secant theta substitution. It should be clear that here we use x equals a secant theta, because here we have a to the 2. So we use a secant theta substitution. And we know that by this substitution, the radical equals a tangent theta. And we know that dx equals a secant theta tangent theta d theta. So now let's substitute everything in terms of theta. Dx is a secant theta tangent theta d theta. And in the denominator, radical is a tangent theta. Tangent with tangent, a with a cancels, and then at the end we have only integral secant theta d theta. From integral formulas, if you remember, integral of secant is ln of secant plus tan plus c. Again, our job is to rewrite this in terms of variable x. We don't want to write our answer in terms of theta. So we draw a right triangle again. We suppose here theta. And then this side would be a and the hypotenuse is x again. Because, let me explain this again to you. Secant theta is x over a. From this, cosine theta is a over x, because secant and cosine are reciprocal. So cosine is a over x, and cosine is adjacent over hypotenuse. So adjacent is a, hypotenuse is x. And by the same calculation that we did in the previous question, we can show that this side is radical x to the 2 minus a to the 2. So everything is ready to be substituted here. What is secant theta? Secant is x over a from here. What is tangent? Tangent is opposite over adjacent. So we can rewrite our answer in terms of x. So we have ln of absolute, ln of absolute of secant again is x over a, plus tangent is radical x2 minus a2 over a plus, and this is the answer of this integral. But if you pay attention, we can simplify this answer. It's not really necessary, but you can simplify this. And if you look at the formula for this integral, in some textbooks you can find a formula for this integral. You would see that the formula is similar to this, but it's not exactly like this. I want to convert this to the standard formula for integral of dx over radical x2 minus a2. So this process is not necessary, but it's good to see this process. First, note that in these two fractions here, the denominator in both of them is a. So we can write them as a single fraction. ln of x plus radical x2 minus a2 over a. Now remember one of the properties of ln. ln of a over b is ln of a minus ln of b. Based on this formula, we can rewrite this expression in the form of ln of numerator, ln of x plus radical x2 minus a2 minus ln of a, of course, plus c. The reason that for a we don't need absolute is because we suppose in this process a to be positive. So we have minus ln of a, or if you want you can put absolute for a, but it's not really necessary. Now please pay attention. What is this c here? A constant. What is ln of a? A is a number. ln of a is also a number, a constant. It's not a variable because it has no x. This is variable, it has x, but this is constant. You can combine this constant with c, and you can suppose both of them. So we add this constant to c and we name it a new constant. So we can write our final answer in the form of ln of x plus radical x2 minus a2 plus, for example, c1. Please pay attention. This answer is the same as this answer, but this is a little better form for the answer of this integral. Let me show you another example. Integral from 2 to 3 of dx over x to the 2 minus 1 to the power of 3 over 2. First of all, note that this is a definite integral. And maybe you wonder why we have to use this substitution. We don't have any radical x to the 2 minus a to the 2 here. But attention, we have a radical here. Because x to the 2 minus 1 to the 3 over 2 is basically x to the 2 minus 1 to the 3 inside the radical because of 3 over 2. And as you can see, we have a radical x to the 2 minus 1. So first we rewrite this integral in the form of integral from 2 to 3 dx over radical x to the 2 minus 1 to the power of 3. In this way, it is more clear that this integral, for solving this integral, we can use the secant substitution. It was not really necessary to write this in this form, but it's for ourselves that we want to make it more clear. But what substitution we have to use? X equals a secant theta. What a here is 1. As you can see, we have x to the 2 minus 1 to the 2, or 1. So we use x equals secant theta. By this substitution, we know that the radical would be 1 tangent theta, or just tangent theta. And dx is secant theta tangent theta d theta. Because we want to do this substitution, we have to update the lower bound and the upper bound of the integral. X is 2 to 3. When x is 2, secant is 2. Secant is 2, it means that 1 over secant is 1 over cosine is 2, because secant is 1 over cosine. If 1 over cosine is 2, if 1 over cosine is 2, This means that cosine is 1/2. If cosine is 1/2, theta is pi over 3. What about 3? If x is 3, then secant is 3. If secant is 3, it means that 1 over cosine is 3. This means that cosine is 1/3. And this means that theta is, we don't have any famous angle for 1/3. So theta is cosine inverse of 1/3. This is the only way that we can write theta. So let's substitute everything in terms of theta. Dx is secant theta, tangent theta, d theta. In the denominator we have radical, which is tangent to the 3. All of this is tangent to the 3. So we have tangent to the power of 3. And the lower bound of the integral is pi over 3. The upper bound is cosine inverse of 1/3. Simplify tangent with tangent. Then we have integral secant theta d theta over tangent to the 2 from pi over 3 to cosine inverse of 1/3. For finding this integral of secant over tangent to the 2, we can write everything in terms of sine and cosine. Because secant is 1 over cosine and tangent is sine over cosine, so we can rewrite everything in terms of sine and cosine. Let me remind you, tangent theta is sine over cosine. Secant is 1 over cosine. So we can replace this secant with 1 over cosine, tangent with sine over cosine. So we have, let me continue from here, integral from pi over 3 to cosine inverse of 1/3. Secant is 1 over cosine d theta. Tangent is sine to the 2 over cosine to the 2. If we want to divide this by this goes up and it multiplies by 1. This goes down and it multiplies by sine. Because it's a division and we have to multiply by the reciprocal of denominator. Basically this is 1 over cosine times by cosine to the 2 over sine to the 2. And as you can see, 1 cosine with 1 cosine cancelled, and then we have cosine over sine to the 2. So we can simplify this and write it as cosine over sine to the 2. And then we have an easy integral, pi over 2 to cosine inverse of 1/3 cosine theta over sine to the 2 theta d theta. But what we have to do here? Now a simple u substitution, we can find this integral. Attention, if we suppose sine of theta in the denominator as u, then derivative of u, which is cosine, is in numerator. So here we do a simple u substitution. For finding this integral, we use a u substitution. We suppose u as sine theta. Then what is du? Du is cosine theta d theta, which we have in numerator. If we solve this for d theta is du over cosine theta. So this equals to integral cosine theta over sine is u, so u to the 2 times by d theta. What is d theta? Du over cosine theta. As you can see, cosine with cosine cancels, and then we have integral of du over u to the 2. But we have to update these upper bound and lower bound again. Theta is from pi over 3 to cosine inverse of 1/3. So please pay attention. Theta is pi over 3. When theta is pi over 3, this is the substitution. If we plug in this in here, we can find u. This is easy. But for the upper bound, no, it's not easy. So from this, what is u? U is sine of pi over 3. What is sine of pi over 3? Is square root of 3 over 2. So this is the lower bound of the integral. But what about the upper bound of the integral? The problem here is that the upper bound is not a simple angle. It's cosine inverse of 1/3. And we want to find sine of cosine inverse of 1/3. So let me show you how we can find sine of cosine inverse of 1/3. So theta is cosine inverse of 1/3. Because theta is cosine inverse of 1/3, this means what? Theta is cosine inverse of 1/3, so cosine of theta is 1/3. Because, attention, what is the meaning of this relation? Theta is cosine inverse of 1/3. It means that theta is an angle that its cosine is 1/3. So cosine of theta is 1/3. If we draw a right triangle here, and we suppose here theta, then cosine is 1/3. So adjacent to 1, hypotenuse 3. Cosine is adjacent over hypotenuse. Then by using Pythagorean theorem, we can see that this is radical 8, a square root of 8. Because if we suppose this as x, x to the 2 plus 1 to the 2 is 3 to the 2, and from this x is a square root of 8. Now that we have this triangle, we are looking for what? We are looking for sine of this theta. So now it's really easy to find sine of this theta. Because theta is cosine inverse of 1/3, from here, by looking at this, we wanted to know what is sine of. Look at the substance, sine of theta. Sine of theta, look at the triangle, sine of theta is a square root of 8 over 3. So the upper bound of this integral finally is the square root of 8 over 3. This example is a really complicated example. You need to know many different things, from trigonometry to substitution to integration, combining all of this. Now finally we are ready to find the value of the integral. Integral of du over u2 is basically integral of u to the negative 2 du, and this equals to u to the negative 1 over negative 1, and this equals to negative 1 over u. From radical 3 over 2 to radical 8 over 3. If we substitute radical 8 over 3, then we have negative 1 over radical 8 over 3 minus would be plus 1 over radical 3 over 2. This can be written as negative 3 over radical 8 plus 2 over radical 3. And this is the answer of this integral that we had here. The value of this integral is this. I highly recommend you to review this example. I know it's so complicated, but you can learn many different things by this example. I hope by watching this video you have learned about secant substitution, and now you know that when you can use this type of substitution. If you like this video, please subscribe in my channel, and see you in the next videos.